So welcome everyone to today's seminar. Today we have Job Feldbrugge from the University of Edinburgh in the UK. Job is a theoretical physicist working at the intersection of cosmology, quantum theory, and mathematical physics. His research applies tools such as catastrophe theory and Pickard-Leschet theory, which I don't know how to pronounce, to problems ranging from the nature of the cosmic web and astrophysical lensing phenomena in wave optics to real path integrals in quantum cosmology. After completing a PhD at the Perimeter Institute in Canada, he held a postdoc position at the Carnegie Mellon University in Pittsburgh, and he is currently a Higgs Fellow at the University of Edinburgh in Scotland. Job is going to be talking to us about unraveling the cosmic web with caustics. So thank you so much for accepting our invitation. You may start when you're ready.
Thank you very much for the invitation. It's great to be here, only remotely. I will be talking about a mathematical description using caustics, which are mathematically described using catastrophe theory, about the cosmic web. So the largest structure in our universe, consisting of the empty voids, the dense clusters, the walls, and the filaments, which we have been observing over the last decades with ever more precision. This is work which I've been doing over the last, let's say, 10 years with Rien van der Wijgaard, Celine Boom, who you might know, and a fantastic set of PhD students, so in particular Benjamin Hedge and Maya Rodriguez, who are currently in Edinburgh, and Amelie Reed, who is in Sydney University. And I will be exploring the general topic of trying to understand the cosmic web from first principles, and be showing some of their recent work, which I think is really exciting. If you have any questions, just interrupt me, ask questions, and rather have something be understood than that I make it till the end of my slides very quickly. So let's start. Let's see whether I can go to the next slide. Yes. So the cosmic web. So with redshift surveys, we have been observing the cosmic web in ever more detail, and we have seen that galaxies are not randomly distributed. Rather, they form this web-like structure of these voids, empty voids, clusters, filaments, and walls. And that gives us a puzzle, because on the one hand, we know that the initial conditions as observed in the cosmic microwave background radiation field are close to a Gaussian random field. So here we have on the left the Planck satellite map, which we of course treasure in cosmology, which is very simple. It's just statistical fluctuations. It's just a multidimensional Gaussian distribution, if you will. Yet, if we let gravity take hold on these fluctuations, we see that you get this highly rich geometric structure, which is the cosmic web. And of course, you can run an embodied simulation and say that's nice. You can start from the initial conditions and embodied simulation, translate that into the cosmic web we see today, or something resembling it. It would be nice, and there's a valid question: how did it come to be the walls, filaments, and clusters? Can we identify local patches in the initial condition space by which we can predict the protogenitors of the walls, filaments, and clusters, their formation time, their orientation? Because if you have control over this mapping in an analytic fashion, you can ask new questions. You can ask, how did our local universe come to be? You might be able to use the geometry to a greater extent to constrain cosmological parameters. Or you could use it to study galaxy formation in a different way, to systematically investigate how the properties of the filaments and the walls and the clusters influence the subsequent formation of galaxies and their properties. So that's what I will be setting out to try to solve and show how far we have gotten on this idea, this probe. So what are these caustics which I was talking about? If you take the vanilla formation of the cosmic web picture, then you can say, well, let's start at the time when gravity takes over, let's say the time of recombination. The universe was fairly homogeneous, extremely homogeneous at that time. So that's represented by this grid. And then the electric forces decay and the gravitational forces are starting to dominate. And what we see is that the overdensities cluster and the underdensities become less dense. And you see that the particles in the embodied simulation, this is just a two-dimensional embodied simulation, start to move. In the process, they form this thing which is resembling the cosmic web, where we see the formation of, in particular, multi-stream regions. So what is a multi-stream region? A multi-stream region is a position in the current universe where multiple particles from the initial conditions move to. So for example, here we see a filamentary structure, which is a three-stream region, because there are three different points in initial space which maps to these positions. And if you can understand the cosmic web in terms of the single and the multi-stream regions, you are along the way to understand the geometry of the cosmic web in a new way, which is what we have been trying to do. So in particular, the caustic which you probably are most familiar with is shell crossing. So the places where the mass elements are turning inside out and the density spikes can be seen in the red curves here. So initially on the upper left corner, you see that it's a universe which starts to develop but hasn't developed any multi-stream regions. If you go to the upper right plot, then you see that a little bit of the matter has started to clump together and has overshot. So it's a little bit like smoke. The particles don't feel each other directly because it's collisionless matter. They only experience each other's presence due to gravity. So they are going to crash into each other, but they overshoot. And that's where you develop these multi-stream regions. So if you look at the lower right panel, then you see that you have a fully interconnected cosmic web, which is outlined by these red curves. So you see in the clusters, you have many of these red curves because there is phase mixing and many shell crossing regions close together. And in the filaments, in this case, you see that the gray areas, which are the multi-stream regions, are bounded by these shell crossing regions. This is the first order caustics. And it turns out that there is a classification in mathematics, which is known as caustics theory, which basically extends this, and that's what we will be using in a second. So this is not a new idea. In the 70s, Arnold in the Soviet Union developed catastrophe theory and extended the work by René Thom from France and developed this classification of these caustics. And then together with Zeldovich, who of course know and love in cosmology, combined these two efforts and basically realized that the structure which emerges in the cosmic web can be classified using these caustics. This was done around the time that the first embodied simulations started to appear. So at the time, it was really a way to look forward and say, well, we have these initial conditions, which is this Gaussian random field. We know that gravity is nonlinear. What kind of features are we expecting? And they used catastrophe theory in order to do this. And even though they were trying to do it to the three-dimensional cosmic web, they could only do it in 1 and 2 dimensions due to some technical complexities, which I will come to in a second. But what the idea they had is if you describe your embodied simulation or your dark matter in our universe, basically from the time of recombination when everything is very, very, very homogeneous to the current universe using Lagrangian fluid dynamics, meaning that you are considering the mapping from the initial condition space when the universe was homogeneous to the current distribution of the cosmic web, through the Lagrangian map, which is this map xt. So what this map is it says, well, at time t, the particle which started at position q moves to position xt of q. And it does this by moving a displacement s. So if I use my cursor for a second, let's see. It's really this equation which is key. So the point starting at q moves to x in time t by executing in displacement s. So this is the key equation which is going to power all of my discussion. So that's what I want to be really clear. So what you can do is you can say, well, if I have such a mapping, then you can look at what the density at the final time would be. And what you find is that it's a change of coordinates. So it is becomes natural that you have to look at the Jacobian. So what you find is that as your fluid is moving, the mass elements which you are describing preserve their mass but change their volume. And their volume is given by the Jacobian, which is in the denominator of the density formula. So what you find is that the density at a given point in your embodied simulation is given by a sum over all the initial positions. So that's the sum which you see on the lower left. And for each mass element which maps to this position x prime, you have to calculate the mean density of the universe divided by the absolute value of the determinant of the gradient of this map x. And now something important can appear, because this determinant doesn't have to be non-zero. So what you will find typically is that you start from a universe which is homogeneous. So you find that x is equal to q, and the gradient of x is 1. So you retrieve your original density field. As the particles start to evolve and multi-stream regions start to appear, the denominator of the density factor can become 0. And this is what we know as shell crossing. And at these instances, the density spikes to infinity, only when you use cold dark matter, but still, it is an enormous enhancement of your density. And what you see in the upper right panel is a plot from this original paper by Zeldovich, Arnold, and Sergei Shandari, where you see on the horizontal axis the position in space. So it's the current universe position in a one-dimensional model of our universe. On the vertical axis, you see the density, and you see that it spikes to infinity exactly when this denominator becomes 0. But there are two different ways in which this caustic has occurred. So on the left, you see two what we know as fault caustics, which are labeled by A2. And on the right, you see a caustic which is an A3 caustic, which is a cusp caustic. So the fault caustic on the left is a caustic which we will recognize as shell crossing. But the rightmost caustic, which is one level up, which is the cusp caustic, is actually of a slightly different nature. And it's really these caustics which will carry us from the initial conditions to the current cosmic map. So how does this work? We have this initial field, Q. It maps to the field X, let's say via an embodied simulation. And we are calculating this density field. And if you calculate this density field, you get a very sharp rendition of our local universe, where you see beautiful filaments and clusters emerge, which are bounded by these regions where the density spikes, which are exactly these caustics. This density field was calculated with the phase-based Delaunay tessellation field estimator, which is a new density estimator which you can download and you can use yourself. And it allows you to get very clear renditions of your embodied simulations to really understand what is going on and to estimate the density with a lot more fidelity. But what we're really interested in is tracing these different caustics, tracing where the multi-stream regions are forming, because this determines the geometry of the cosmic web. So how should you visualize this? You have this initial sheet, which is in Lagrangian space, which can be seen as a homogeneous manifold. It's just a plain sheet in space. As time evolves, the sheet will start to deform because the particles are starting to move. And as a consequence, the sheet will stretch and will deform. And this is what I visualize here. So you see that it starts to stretch. The mass element on the right went to the left, on the left went to the right. And you see that you have a development of a multi-stream region because there are multiple particles. Vertical is the momentum, which map to the same final positions. And the boundary between the single image region to the multi-image region is given by this yellow contour, which is exactly the shell crossing region. This is the place where the denominator of the density field spikes to infinity. But now if you look carefully, then you see that this curve, these lips, are consisting of two arcs, which indeed are the fault caustic. But you also have two tips. You have a tip on the top and a tip on the bottom. And this is a non-differentiable point on this manifold, and that is actually the cusp caustic. So this is the first kind of introduction of the geometry of this cusp caustic. And this is what we will be tracing. If you do this in 3D, then you should imagine that you have a three-dimensional volume, and some particles are moving to the left and some particles are moving to the right. And again, you have a boundary between the single image region and the three-stream region. I should say single stream region. And what you find is that the boundary between this three-stream region and the single-stream region forms the so-called Seldovich pancake. So here you see that the blue surface is the shell-crossing region. This is where the mass elements are turned inside out. This is where the density in colored matter spikes to infinity. And around that you see this rim, which is the multidimensional extension of these 2 points which we saw before. And this is the cusp caustics. So you should visualize this as an UFO and out of the cartoons in some sense. So a flying sorcerer where you have a rim, and that is the cusp caustic, and the surface of the dishes is the fold caustic, which is the shell crossing regions. And the beauty is that there is this mathematics which classifies all these ways in which these singularities occur in the projections. And I won't go into the depth of the mathematics, but the important thing is that there are only a finite number of ways in which a singularity can occur when you consider a mapping from three-dimensional space to three-dimensional space. What you can find is you have the so-called fold, cusp, swallowtail, and butterfly caustics. And in addition, you have the hyperbolic, the elliptic, and the parabolic caustic. So if you charge, it's like learning a new language and you only have 7 words to learn. So it's a very simple language in some sense. So if you have such a mapping from initial condition space to final condition space, and you're interested in the way in which this mapping can become singular, which is exactly when this density spikes to infinity, there are only 7 ways in which this can happen. And now the beauty is that there is a mapping between these different caustics. So you have the fold, the cusp, the swallowtail, the butterfly, the hyperbolic, elliptic umbilic, and the parabolic umbilic, and the structures in our universe. So what we have is the fold caustic corresponding to collapse regions. You have the cusp caustics, which will correspond to the two-dimensional membranes in our cosmic web, which are the cosmic walls. You have the swallowtail caustics, which correspond to filaments. And you have the butterfly caustics, which correspond to clusters. In addition, we find that there are also hyperbolic, elliptic, umbilic filaments and parabolic umbilic clusters. So this is kind of the summary of catastrophe theory. This is the list which you get if you go to your mathematics friends and ask them about the singularities which can occur when considering mappings from three-dimensional to three-dimensional space. And the reason that this is useful is because we can turn this into a way of understanding structure formation. So what I was saying before is that what we are considering is the mapping from initial condition space to the current universe, from Lagrangian space to Eulerian space. And what you can do is you can say, well, if I consider this space, then let's look at the mapping between them. So the left plot here corresponds to the initial condition space. So that should be your CMB, your cosmic microwave background radiation field, the fluctuations which we see in the initial universe. On the right is the Eulerian space, so that's represented by X, which is our current universe. That's what it's meant to represent. So now the key point, which I worked out several years ago, which allows us to extend Arnold's work and Zeldovich's work to 3D, is to say, well, let's consider an arbitrary curve in initial condition space. So that's that red curve C, which you see in the plot. Let's now take all the points on this curve and map these to the current universe. And what you now see is that at some points you develop a discontinuity, you develop a kink in the curve. And this can happen for curves, but it can also happen for sheets, can also happen for three-dimensional volumes. And what you can ask yourself is, under what condition do I develop such a non-differentiable point, which is here QS? And it turns out that that's a combination of the eigenvalue fields of the deformation tensor and the eigenvector field of the deformation tensor. So we are very used to considering the eigenvalue fields because that's what we have in the denominator of the density field. But the eigenvector fields are normally ignored. So we see that we need a condition which describes the geometry of these foldings which happen when you consider the mapping from the initial condition space to the current universe. And these are completely governed by 1 plus the eigenvalue field, 1 plus mu, which is the eigenvalue field, times the dual of the eigenvector field inner product with the tangent vector of this manifold in the point which developed this caustic. So if we apply this to our embodied simulation or to our universe, then what we find is that you can get a whole list of conditions which mark exactly when which elements in the initial condition space are undergoing these foldings and are undergoing these caustics. So what you find is at first that if you look at the density formula, which we had a few slides back, and you see the density formula is 1 plus mu times 1 plus mu 2 times 1 plus mu 3. So the density definitely spikes when 1 plus mu is 0. And indeed, you find that this is where the fold caustic lies. So if you look at the first condition, then you say, well, all the initial points which have 1 plus mu is 0, they are corresponding to the fold caustic. These are the shell crossing regions in your embodied simulation. If you now look at this shell crossing region and you apply this same formula, this 1 plus mu times the dual of the eigenvector field times the tangent of this manifold is 0. If you apply that condition to this fold caustic, then you get the cusp caustic, which is this sharp rim which we had a second ago, which is the condition that the directional derivative of the first eigenvalue field in the first eigenvector direction is 0. So that's where the eigenvectors start to come in. And if you keep doing this, you get this whole list of different conditions, which are conditions on the initial conditions. So that means in Lagrangian space on the Gaussian random field we started with, which mark how the different singularities are forming and how the different filament clusters and walls are emerging in our embodied simulations or in our universe. So this is a classification of the current cosmic web used based on the formation history of the filament clusters and walls, which is completely based on these eigenvalues and eigenvectors, because these really describe how the space is stretching and contracting and forming the multistream regions which we see today. So again, you have this list of caustics, which is a finite list, which is a triumph of the 20th century mathematics, which we can turn into a way of understanding how our walls, filaments, and clusters are forming. And we expect that the density field around them will be different. So they should be seen as markers of local environments of our cosmic web. So this, I completely understand that this is very abstract mathematics. So the rest of my talk, I will try to show how this actually materializes in simulations and in our local universe. So if you have any questions about this, please ask. Happy to explain anything which is unclear. It's muted. Shall I just continue?
Yes, please continue.
Yes, please.
All right. So what I was saying before is that these eigenvalues and eigenvectors are really important. And you can see this directly. So if you take your initial conditions, let's say a two-dimensional model of our universe, then you can sample initial conditions, which is a Gaussian random field. So these are the initial conditions. You can calculate the gravitational potential. So the density field is the upper left plot, corresponding upper right plot is a gravitational potential. Normally what we do is we calculate the Hessian at every point in the gravitational potential. And then you know that the trace, so that the sum over the diagonal using Laplace's equation is the density field. If you calculate the eigenvalues and the eigenvectors instead, you get the lower two plots. So you see that the sum of the eigenvalues has to be equal to the upper left plot, which is the density field. But you see that the eigenvalues split the density field basically up into two components where you see all these worms, you see all these lines. And these lines are indeed the progenitors of the filaments in our universe. So what we can do is we can take the Zeldovich approximation, which is the linear, first order linear approximation of structure formation, which is given by the upper left plot. So we see that the final position is the initial position minus the growing mode, which is just a natural time parameter, times the gradient of the primordial gravitational potential. And we compare that to an embodied simulation. So you see initially the plots are very similar, but as soon as multi-stream regions start to appear, you see that the Zeldovich approximation, which is the left plot, puffs up and it's not very reliable. It's not very reliable at estimating the density field. But the caustics, which we were talking about, are still markers of how these different nonlinear structures emerge in the embodied simulation. And to show this, let's take the initial conditions of the Zeldovich approximation, so the left panel, calculate the Hessian, calculate the eigenvalue fields, and in particular the first eigenvalue field, the largest eigenvalue field, is here plotted on the left. So you see this worm-like pattern. If we now calculate these higher order caustics, which are these nonlinear equations in terms of the eigenvalue fields and the eigenvector fields, then we get these lines and points on the left. If we now take these lines and points which live in the initial condition space, so the beginning of the universe, the time of recombination, and we map them onto the embodied simulation using the two-dimensional embodied simulation, then you get the right plot. So you see everywhere where you, by eye, would identify a filament, everywhere where you have a multi-stream region, it's nicely bisected by these red lines, which are predicted basically from the Zeldovich approximation, and these blue lines, which are bisecting these regions, which are nice traces of the filaments in this two-dimensional embodied simulation. So this is an illustration where we have identified the progenitors of the filaments and the clusters from the initial conditions without using the embodied simulation. And this is really showing why this is powerful. So you can do this in 2D, which is nice to visualize, but of course we want to do it in 3D. And if you take a very small three-dimensional embodied simulation and you look over time, then you see that initially you have a few multi-stream regions formed, which is the upper left plot. And as time progresses, they grow and they interconnect to form the walls and the filaments of the cosmic web. So here you see the density field in the blobby rendition, and superposed you see how the cosmic web, the caustic skeleton of the cosmic web is slowly growing. So this is purely using these 5 equations in terms of the eigenvalue fields and the eigenvector fields. You can split them out. So here on the left we see just the particle distribution of an embodied simulation. On the central plot, you see the filaments, and there are 2 different filaments predicted. So you see the blue filaments, which are the swallowtails. You see the umbilic filaments, which are the red filaments. And we expect the swallowtail filaments to be forming earlier, to be thinner, to be longer, and the umbilic filaments to be thicker, forming later. And they have a different role to play in the cosmic web. So the red filaments on the central panel are the really big arteries. So these are the really big structures which are connecting our cosmic web. But there are all these smaller filaments, which are these blue curves. So you find that there are regions where you have the red curves, but you don't have the blue curves. You have regions where you have the blue curves, where you have swallowtail filaments, but you don't have the umbilic filament, so they are existing in the absence of the umbilic. But if you have an umbilic filament, which is a very thick and important structure, we basically see that the swallowtails are always found nearby. But we expect that the gravitational force of the umbilic is stronger than the swallowtail. So when there is a red line, it's probably dominated by the umbilic filament. But still there exists this whole set of filaments which can only be understood when you take into account the eigenvector fields, which are basically the smaller paths in our cosmic web. So here's another rendition where you see the density field calculated with the phase space method, which I was showing before. And you see, well, the movie runs a little bit jagged, I think. But you're supposed to see that the filaments, the walls and the filaments are nicely tracked and predicted from these very small set of equations. What you can do is you can take an embodied simulation, you can slice it in a plane, you can calculate the density field in that embodied simulation, and now you can just overlay these caustics. So what we find is that these are the red curves are the walls. So if you take the walls, which are 2-dimensional sheets, if you slice it in a plane, then you get curves. And this is what you get. And when I first saw this, when my student Benjamin rendered this, I was amazed because I didn't expect this to work so well. It is based on the Zeldovich approximation, and typically we expect the Zeldovich approximation to break down at fairly large scales. But it turns out that it's more powerful than I at least expected. And the cusps are nicely tracing the sheets in the cosmic web. But when I first showed this, people said, oh, but there's also a lot of structure which you're missing, because we see many excess density regions which don't have a red curve. And by the way, the blue points and the green points are the filaments, but they are more difficult to see in a slice, because if you take curves and you slice it in a plane, then obviously you just get points. But the important thing is that we realized that here we cut the the caustic skeleton off at what forms today. So we look at the regions which in the Zeldovich approximation form multistream regions today. But if we look forward and we basically look to the regions which have not yet multistreamed, then you get this. So here you're basically looking forward and you say, well, these regions, these particles might not have formed a multistream region yet. But if gravity would, if the cosmology would evolve as we expect, then actually they will form multistream regions. And then you see that basically most of the structures up to, let's say, a megaparsec can be understood from the initial conditions using these caustics, which I think is a remarkable fact. Normally, we treat and embody simulations as black boxes, which transform these Gaussian fields to the current cosmic web. But it turns out that a lot of information could already have been extracted from the initial conditions. So by combining embodied simulations with this theory, I hope that we can develop a new language and better way to understand the geometry of the cosmic web from first principles. We can consider the cosmic web at its finest scales, being sensitive to all the small fluctuations and all the small filaments. But of course, if we are doing observations, we might be only sensitive to the largest structures. And for this reason, it's useful to consider this skeleton in scale space. So what we do is we take the initial conditions and we smooth it with a Gaussian filter. And you see that in the upper plot, you're sensitive to basically all the structures which are there. But if you are turning on the smoothing, then you become less sensitive. And here, for example, in the left plot, the lower plot, you see that there is this wall which is going from the bottom panel to the upper part of the plot, which is really a massive wall. And by smoothing, we can distinguish, we can prioritize which parts of the cosmic web are more dense and more fully developed, and which parts are more subtle and more fine-grained, so to say. So this is how we propose to take into account a hierarchy of structure in a cosmic web, because we know that walls are not made out of brick, but they are more made out of smaller walls and filaments. So you need a way to regulate the scale in your simulations. So here's a rendition of the TNJ Illustrator simulation, where we have calculated these sheets and the density field, and we see how the arteries, the filaments, are basically picked up with more detail if we are decreasing the smoothing length. So this is a rendition by Benjamin, my PhD student, and you basically can have a new way of understanding the cosmic web, because it's not just an overdensity, it's a region of space which has an history, and we can look in the history by tracing these different caustics. You should really see this caustics as a family history of these different structures and how they are related. If we calculate the halos in the illustrative simulation or in the embodied simulation in general, to basically go towards the galaxies, then what we see is that these halos nicely trace the different caustics. So when I first started this work, I saw many small grained filaments, which here are given by the very light yellow lines in the right plot. And for a long time, I was looking at them in my computer and I thought, well, that's nice, but it's probably not real. But to my big amazement, recently we calculated the halos, we overlaid the halos over the skeleton, and we see that the halos picked up in the embodied simulation indeed nicely trace these filamentary structures. So again, these are swallowtail filaments, which are given by the eigenvector fields and the eigenvalue fields, which are not part of the classic classification in terms of sheets, walls, and filaments using only the eigenvalue fields. And we see that the halos can be, the location of the halos, the halo bias in some sense, can be understood to some extent by tracing these caustics in a small scale and seeing how they feature. So you can see that in different simulations, and this is something which we have come to realize that it's a universal part of the structure. You might say, well, I see a few dots which are halos, which don't seem to link to the density field, for example. But if we plot it in 3D rather than a slice, then we do find that there are caustics also associated to them. So when you are representing a three-dimensional structure as a two-dimensional field, you always have to compromise in a sense. And in this case, that's basically a compromise we had to make. So it's nice that we have this prescription, but can we actually use it in a practical way? Well, one way to do it is using constraint simulations. So what we have here on the right is a two-dimensional simulation. In the yellow curve, the blue curve is the cusp caustic. So that's the A3, that's the one in 3D, which corresponds to the sheets, and 2D corresponds to filaments. And on the left, you see the conditions which these curves satisfy. So you see that the first eigenvalue field has to be 1 over the growing mode. You see that the directional derivative of the first eigenvalue field in the first eigenvector direction has to be 0. And you can also calculate what its normal is. So when I did this for the first time, I imposed these conditions on my initial conditions on my Gaussian random field. And I was really disappointed because more often than not, my filament turned out to be a cluster. And this turned out to be the case because the Zeldovich approximation is not really trustworthy when you have clusters. And you can see that because the blue line gets tangled up in the clusters. And moreover, the clusters act like vacuum cleaners. They are like black holes. They are attracting a lot of matter. So if you would drop an arbitrary point in your initial condition space, more likely than not, you will be in a cluster, just because so much matter is in the clusters. So what we decided to do is to take a more dynamical approach. So you say we have these cusp lines, which are the filaments in 2D, and we don't want to sample an arbitrary point on that blue line. Rather, we would like to have a center of the filament. So we want to say, oh, if the two red blobs on the left and right are two clusters, then there is a filament in between, which is the blue tube. And in between the filament, in the middle is a point where basically it's maximally stretched, because all the matter on the left is going to the left, all the matter on the right is going to the right. So there's a kind of a dynamic point in between where matter is stretched, and that's kind of what we define as the center of the filament. So if you go through the mathematics, then you get an additional set of conditions, which are listed here in terms of the second eigenvalue field and the second eigenvector field. If we impose these in the initial conditions, and this is the list of conditions you would get in 3D, then what you get is beautiful realizations of our cosmic web, where we have basically grown, in this case, a wall in the cosmic web. So if you look at the upper panels, these are 3 slices through the wall. So in the upper left plot, we are slicing the pancake, the wall, along its structure, its wall structure. So you see that there is a beautiful planar structure in the upper plot. If you take the central upper plot and the right upper plot, there we are taking this wall and we are basically slicing it along this direction or this direction. So you really see that it's a pancake-like structure, it's a sheet-like structure. You can also see this in the lower plots, where we calculate the number of streams. So you see that the blue point where we impose the constraint is in a 3-stream region. It's in the center of the wall, and on the left and the right you have 2 filaments, which are in the yellow color. And this is really when you slice it in the plane of the filament, if the wall. In the other 2 plots are, of course, orthogonal slices, so you see a lot less. You see just a very thin structure, which is what you expect. So this is a way in which we can now simulate these structures systematically, and we can ask the question, how do halos, how do galaxies behave near such a filament? And is a filament which forms early different from a filament which forms yesterday? So also the age of the filaments in the cluster tends to influence the density field and presumably will influence the galaxy properties. So we just published a paper on the illustrious simulation where we saw that the galaxy properties are indeed influenced by the age of the structure which is forming. So for an old filament, we expect more reddish galaxies. And for an early filament, a filament which forms yesterday or a filament which is going to form tomorrow, we expect that the filaments are bluer. And this is, of course, not surprising, but it's nice that we can now systematically study and acquire this in the embodied simulation, because the definition of the cosmic web is now completely tied to the formation history and the dynamics, and not a prejudice of the theoretician. It's not like I woke up yesterday and I thought, well, filament is probably a little bit longish and a line-like structure. No, this is really what the mathematics is predicting. When you take into account that you have a Lagrangian fluid which develops singularities, then these are the conditions you get. And there's very little wiggle room and tuning room. This makes it mathematically difficult because sometimes it forces you into a corner where you cannot, well, you have to work very hard to get out again. But this is what we have been trying to pursue. Here you have a rendition of this wall, which is where the constraint is set on the big blob, the yellow blob, the white blob in the middle, where you see that you get this beautiful thin sheet-like wall. And this is what we did for the walls, and currently we are doing this for the filaments and the clusters, where we are really interested in seeing how the different filaments are materialized and how the different clusters are materialized as a function of whether they are of the A type or the D type, and whether they are early or late forming structures. So that's ongoing research. Something which I'm really excited about, which happened really recently and was done by Amelie Reed in Sydney, is she took the reconstructions of our local universe based on the 2-mass survey. So the 2-mass survey is an all-sky survey of our local universe. And here you see the galaxies in this survey. And the Borg team, the Aquilaia team, who developed the Borg reconstructions of our local universe, what they did is they took these initial conditions and they basically ran them back to the initial conditions. They got 50 samples of Gaussian random fields, which, if you run an embodied simulation, get a structure which is resembling our local universe. So you get the Coma Cluster, you get the Perseus-Pisces, and this is an example of these reconstructions. So here you see in white you saw the galaxies which are in the 2-mass survey. This is the Manticore simulation, which is an embodied simulation run on these initial conditions. This is in the Cosmic Twin project. If you go online, you can actually just download these simulations. So you find 50 simulations which resemble our local universe. And what we have been doing is we have been taking these simulations and we have been calculating the caustics in them. So here you see 3 different samples from these 50 embodied simulations. And you see that there are differences between these simulations on small scales, but on large scales they are largely coherent. So the different simulations predict the same structure. So presumably that is a fair representation of our local universe. So this is the Coma Cluster. And what we can do is we can calculate the caustics as a function of the smoothing scale of the Coma Cluster. So this is in particular the stickman, which we know and love in cosmology. So on the upper plot, you see on the background, you see the density field in real space, and superposed, you see the caustics, which are overlaying it. On the bottom plot, you see the same plot, but then in redshift space. So this is where we can actually overlay the galaxies, which are the orange points. And you see that the galaxies are somewhat tracing the caustics, which are predicted from these reconstructions. You can visualize them in multiple ways. And here we see the Abel clusters in the red circles. And you see that they are nicely linked to the different structures. So now we can say, well, we have this Abel cluster in our local environment. When did this region shell cross? What are the initial conditions which led to that structure? So we find that the Coma cluster and the stickman are a very dense and virialized region, which is primarily dominated by the swallowtail filaments. And what we find is that, for example, the Perseus-Pisces cluster, or Perseus-Pisces wall, I should say, is a far more nebulous structure which formed at a later time and which is more where the galaxies are closer to the umbilic filaments. So this is all still very preliminary research, but we find that there are indeed different regions in our local universe which are dominated by different caustics, where the structure formation is governed by different ways in which these singularities form. And that's something which we are really excited to explore in the coming years. So this is again a rendition of Pisces-Perseus, where on the top you see the caustics in green, and here the color in the caustic is basically the distance the filament is in the direction into the board. So based on the color, you can have a little bit of feel for the depth. And the orange points are really the galaxies in the two-mass survey. And for example, one thing we are really excited about is to take this prediction of our structure in the local universe based on the Millennium simulation and, for example, compare them to different and more detailed redshift surveys. So it would be great to compare this, for example, to the Euclid survey or the DAISY survey to see whether we can understand or predict the structures which we see in the more recent surveys from the caustics which are underlying their formation history. So with that, I would like to conclude. So I hope to have shown you that by considering the geometry of the cosmic web, and in particular the folding of the dark matter particles in phase space, you can get a different perspective on structure formation, which yields a very crisp and clear definition of the different elements of the cosmic web. So the walls, filaments, and clusters really roll out of catastrophe theory because they just happen to be different singularities of different dimension. And in order to understand this, you really have to get a handle of not only the eigenvalue fields, which we use very often, but also the eigenvector field. It's really the combination of the eigenvalue field and the eigenvector field and their geometries, which unlocks these higher order caustics. So that allows you to go beyond just shell crossing, and it allows you to get, for example, the cusp sheets and the swallowtail filaments. I hope that this will improve our understanding of the cosmic web and ultimately help us to understand galaxy formation better, because it might be a way to bridge the gap between the cosmic web and the formation of galaxies and allow us to systematically study them. So we can run 100 simulations of one type of filament, and we can look at what galaxies will be around it, and then we can take a different filament and look at how the galaxies are typically behaving around these structures, for example. And finally, I hope that we can use this to study our local universe using these constrained embodied simulations. But ultimately, we would also love to apply machine learning to this. So you can imagine that you run 100 simulations, very small scale simulations, where you have primed the initial condition to form a certain structure. And then you can teach a computer, well, this is how a filament forming at this formation time with this length scale looks like. So can you now recognize this in real data? That's kind of the holy grail at the moment, because that would allow us to run very small embodied simulations, considering different gravitational parameters, for example, and see whether we can be sensitive to these in the redshift surface using the geometry. So this is very complementary to the techniques which are commonly used, such as endpoint correlation functions, which are not so fine-tuned to understand the geometry of the cosmic web, because they don't take into account the formation history. So with that, I would like to conclude. Thank you for attending. If you have any question, please ask now or send me an email. I'm happy to talk.
Rafael.
Can you hear me well?
Yes.
Yes. So thanks for the nice talk. Celine told me about this work last year, so I really like the approach. I have many questions, but maybe focus in two. One is, I will try to simplify the language just to be intuitive. So we have this taxonomy of caustics that constrain how basically the initial conditions of a given dark matter fold. So the first question is it feasible to bring memory from the dark matter model in the sense, because I think there's some assumptions about how they distribute in the phase space. But let's say you have some sort of, anyway, some dispersion there. I think Celine likes this alternative model. So can you carry memory from that in the way that you could use that as a constraint or a limitation to different models because they wouldn't be able to create certain types of structures or something like that? Is there something to bring also to these assumptions about the... Yeah, that's the one, my first question.
Sure. So indeed, this is a taxonomy of the different ways in which you can form these structures. And it's really important to realize that this is not a physics theory, it's a mathematics theory. So it's a different language to understand the cosmic web. So indeed, you can now take a physical model like Celine likes to explore using different dark matter models, for example. And you can try to see how do these caustics differ between them, and is there memory between these different structures. So indeed, so we haven't done this, we haven't even started that, but in principle you can try to study these theories indeed using this formalism. And the hope is that we can do it very systematically because we know exactly how to generate initial conditions which have this particular caustic in the center of the body simulation.
My second quick question, when you go to like more to the observational side, there will be photometric redshifts, there will be selection bias, there will be a lot of noise to be able to touch. So is there, yeah, I just would like maybe if you could comment about how you guys plan to attack that for Euclid or things like that.
Yeah, so these problems are of course very real, and I completely realize that it's an ambitious goal. So what we currently are doing is we are using these reconstructed initial conditions. So these Borg reconstructions using the Manticore simulations. And that's one way to go about it, because you're basically outsourcing all these issues to the reconstruction of the initial conditions. But it's also very limiting because then you are tied to lambda CDM and whatever model people use to generate these initial conditions. So what we ultimately would like to try to do, and we have started this, but this is something which will take time, is to run constraint simulations, as I described, and then apply a model for the redshift space distortions, to the biasing, to all the effects which you just mentioned, and then to see whether we can still get a computer to recognize these in the redshift surface. So the goal would be to take a simulation and basically corrupt it or deform it, or however you want to phrase it, to take into account all these biases and all these systematics which we're having, and then to see whether we can still recognize them. Because I can now, after doing this for many years, I can recognize these structures by eye, but it's a not very objective way of doing it. So in the end, we would like it to be systematized and to have a machine basically recognize these structures. So that's our current goal, but we have to see whether we actually get there, of course.
Thanks.
Questions? I have one. Students, think of one. Okay, so thank you for your talk. I thought it was super interesting to see all of this fitting. You showed that you applied to the TNG simulations. Which one? And my question is related to how into the local universe you're going. If things continue to make sense and fit when you go to like galaxy scales and filaments around galaxies.
Yes.
If you do a TNG 50, you have more resolution, and I don't know which one you applied it to.
So the cosmic web was calculated just using the dark matter TNG simulation, so a very cheap one. For the galaxies, I believe we used TNG 50. But the the more important question is, of course, to what scale does this actually apply? And can we go to the galaxy scales or filaments around these galaxies to the smaller scales? And at the moment, we believe that you can use the Zeldovich approximation with this mathematics to go to, let's say, 1 megaparsec. So that's not small enough to really understand galaxies, obviously. But what we are hoping to do in the coming year is to go to higher order Lagrangian perturbation theory. So you can do 2 LPT or 3 LPT or 4 LPT. And presumably, if you go to higher order perturbation theory, you will be able to go to smaller length scales. So in principle, it should be possible to predict these structures for smaller length scales using the initial conditions, but that's yet to be seen. What you can do is you can take the embodied simulation itself and detect these caustics in the embodied simulation. So you're not predicting from the initial conditions anymore, but you are just visualizing in the embodied simulation. And this is something which we started to do, but it has numerical instabilities. You have to be really careful that you are not dominated by noise. But in principle, you can do that, and then there is no limitation. So then you should be able to apply to any scale you like. But we started the simplest thing which we could think of, which was just Zeldovich.
Any more questions? If not, let's thank Job again. Thank you.
Wow, that's a difficult job.
Job, the stream will be on YouTube, okay?
Perfect.
Thank you.
Thank you. Have a good day.